Welcome to MEI Numerical Methods, Solution of Equations 1. In this video we'll be looking at the method of false position. This method is sometimes known as linear interpolation and can be an improvement on the bisection method. So suppose that we have an interval AB and we've discovered that there's a change of sign in the function in that interval. Then, whereas for the bisection method we would take the midpoint of A and B next, for the method of false position we were going to treat the function as being approximately linear between A and B, so that although the true point of intersection of the curve with the x-axis is as shown there, we're going to be finding out this point C. And we're going to see in a moment that this is the point C is given by this formula here. So we can prove this result by using similar triangles. So in this diagram, which is just an enlarged version of the main part of the previous diagram, we've got two triangles. So we've got the call that triangle 1, future reference, and triangle 2, and if we label that angle theta, then that's going to be theta as well, and we can see that the side FB in triangle 2 is going to correspond to the side f of A, or minus f of A, in triangle 1. The note in this example, f of A was negative, so minus f of A is a positive quantity. It's the length of triangle 1. So there are different ways that you can set up similar triangle equations, but one way is to say that we've got the two sides in triangle 1, C minus A and minus f of A, and then the corresponding sides in triangle 2 are B minus C and f of B. So you might like to pause the video and have a go at this yourself. So we're trying to make C the subject of the equation, so we'll just get rid of the fractions to start with. And then this leads simply to the formula above. So this is the example we used when we were doing the bisection method. So we've got A being 1 and B being 2, and we found the value of the function in those two cases, and so you might like to have a go at this yourself. But plugging in those values, gives 1.17 to 3 significant figures. So the process is exactly the same as for the bisection method, and our value of C that we found on the previous slide gives rise to a value of the function which is closer or smaller, and so it's closer to the x-axis than when A was 1, so that gave a value of -1. So we're now at minus 0.5787, which means the left-hand limit can be replaced with our value of C, and the right-hand limit stays the same, and in this example we can see that it always stays the same. If you consider the curve looking like that, then if we the line's always going to be to the left of the curve, and so our estimate is always going to be to the left of the true value. So as our estimate increases as we go down the table there, it's going to converge on the true value from below. So one of the drawbacks of the method of false position is that you get a fairly wide interval. So here even down here at the bottom we've got an interval 1.324279 up to 2, and although the 1.324279 is a good estimate for the solution and maybe a better estimate than we'd have for the bisection method, we do have this problem that we haven't got an interval or a convenient interval in the same way that we have for the bisection method. But you can always get around this problem by just going slightly to the right of that value, and until you get an x value where you get a change of sign. So we're negative at a negative value of the function for that value of 1.32, etc. And so we just need to find a value to the right of that which has a positive value for the function. So that concludes the video on false position method part 1, and we'll be looking at some other ways of interpreting the method in the next video.